Hi, welcome back to another Pharmacy Republic video. Today we'll be talking about low dose naltrexone or LDN. The first thing to bear in mind when discussing LDN and how it works is that it's an unlicensed medicine, which means it's not available off the shelf. It's not available through the usual channels. You have to get it made specially from a compounding pharmacy or a specialty pharmaceutical manufacturer. Also, because it's an unlicensed medicine, not many doctors are aware of the potential benefits for sufferers of chronic fatigue syndrome and fibromyalgia and other autoimmune conditions. Okay, so what is low dose naltrexone? As its name suggests, it's a low dose of naltrexone. What is naltrexone? Naltrexone belongs to a class of medicines known as opioid antagonists. The What we mean by an antagonist is that it blocks a receptor. So what will be useful to do now is just to go over, have a quick revision of a few terms so you'll understand what we mean when we say an agonist, an antagonist. Okay, so in our body we have things called receptors, and when we take a medicine, that drug binds to the receptor to produce a response. When we're talking about things that we produce within our body, we call this endogenous. When we take substances outside, like a medicine or a drug, that's called exogenous. So receptors are like docking bays for either endogenous substances produced within the body or exogenous substances produced outside of the body. So if we just have a look here, so we have a receptor, and then we have the thing that binds to the receptor, the drug or molecule that binds to the receptor and produces a response. In this case, that is known as an agonist. Now, when a drug binds to a receptor and doesn't produce a response, but occupies the receptor and stops the agonist from binding, that's known as an antagonist. So it binds to a receptor but doesn't produce a response and stops a response from occurring. That's known as an antagonist. Okay, so naltrexone binds to an opioid receptor. In particular, it binds to a receptor. There's 4 types of opioid receptors. It binds to the mu receptor. So when it binds to the mu receptor, the opioid, whether it's our own endogenous opioids called endorphins, or an exogenous drug like morphine or codeine, then that action of that drug is prevented. We will not get that pain relief, and in fact that's why naltrexone was developed. It was developed to help in the treatment of addiction, in particular the rampant opioid addiction which was occurring in America at that time. In fact, the US government fast-tracked the development of naltrexone to help fight this epidemic, this opioid addiction epidemic. So what happens was when if someone was addicted to heroin, they would take the heroin would bind to the receptor, and they would get that euphoric high. Okay, so when naltrexone was given to such a person, it would occupy the receptor, and when they tried to take heroin, it would not have an effect. And this is how it was used in a lot of addiction programs throughout the US. It was also used to help with the treatment of alcohol addiction. Before we go any further, it would be useful just to have a quick summary of how opioids work to help reduce pain. Okay, how do they act as painkillers? So we have nerves in the body, and you have receptors which monitor the environment and tell the brain when a certain part of the body is injured. Now, we have a number of nerves, and in between, you don't have one whole nerve, you have a gap in between where 2 nerves meet. And this junction, there's nothing in between, so there's this message has to somehow get from the first nerve to the second nerve. So how does it do this? When you get to the terminal of this first nerve, it releases substances to tell the second nerve that an injury has occurred. so that the brain can experience pain. So this first nerve releases something called, funnily enough, substance P. That docks with the second nerve, receptors on the second nerve. Remember we talk about receptors, you've got some here, and that allows the propagation of the message to the brain, and the brain realizes some kind of pain has occurred. So, and it will take action. For example, if we've stuck our finger in a fire, then the brain will say, take your finger out of the fire. So when the brain experiences pain, it also releases its endogenous, remember endogenous means within the body, painkillers, and these act at the first nerve terminal here to reduce the release of substance P. When we talk about opioid receptor, we mentioned earlier heroin. So why do people take heroin? They get a high. What causes that high? Dopamine. We're all chasing our dopamine fix. Dopamine is responsible for that feeling of euphoria when someone takes drugs. So what happens is GABA is a natural brake on dopamine. And opioids, what they do, they indirectly increase our dopamine levels, so we feel high when we take something like morphine and codeine and heroin, hopefully not heroin, but that's why people can get addicted to morphine and codeine, because it indirectly increases dopamine by turning off the brake to dopamine, the GABA. Okay, so now we know something about how the opioids work in pain relief. Okay, let's get back to receptors, agonists and antagonists. So at 50 milligram, the naltrexone, it totally blocked all the opioid mu receptors. Okay, so if someone was to take morphine or heroin, they wouldn't get the high at all. Okay, in fact, it produced something called dysphoria, because it also blocked your natural endorphins, and your endorphins make you feel good. So that was at 50 milligram. Researchers started playing around with the doses of naltrexone, okay, and they reduced the dose to in between a range of 0.5 milligram or 4.5 milligram, and they found something strange occurring. Okay, so this is the occupancy at 4.5 milligram, if you like, or temporary occupancy. Okay, what happened was the brain then looked at the scenario and said, oh my gosh, I haven't got enough endorphins or enough receptors, something must be wrong. Let me make some more. And so what happened was the brain caused more receptors to be made and more endogenous endorphins to be made. This is called upregulation. So by lowering the dose of naltrexone, we trick the brain into producing more receptors and more endorphins. Okay, so how does this help with low dose naltrexone and the benefits that we see in a lot of autoimmune conditions? Opioid receptors, not just to do with pain relief, they're also found on immune cells. And a lot of chronic conditions, autoimmune conditions, are when our immune system starts to malfunction. So on our immune cells, we have opioid receptors. And at this low dose, not at the 50 milligram, at the low dose, we see these potential benefits to the immune system. By upregulating the number of our own endorphins, they dock with the receptor on the immune cells, and they can promote healing. They can reduce inflammation. And in some cases, they can actually inhibit cell growth, which evidence suggests is useful in certain cancers. So there is some evidence from it, but there haven't, because it's unlicensed medicine, there haven't been any large-scale clinical trials. Now, that explains when naltrexone encourages the upregulation and produces our body's endorphins. Okay? It also acts on another class of receptor called a toll-like 4 receptor, which is also present on immune cells and glial cells, which actually are like the scaffolding of nerve cells. And toll-like 4 receptors, when they're occupied, they send out messengers which propagate an immune response. So when a toll-like 4 receptor is occupied, it spreads inflammation. It sends out these cytokines, which are basically loads of little messengers which say, hey, look guys, there's a problem here. We need to increase the inflammation. Okay, so it spreads that inflammatory message. Okay, and again, to do with autoimmune conditions when the immune system is out of control. So how can the naltrexone work on this receptor and this receptor? Two different receptors. How does that work? So let's look at our hands. We've got a left hand and we've got a right hand. They're both hands, but I can't superimpose them because this thumb is pointing to the right and this thumb is pointing to my left. So you can't superimpose the hands. Similarly, the naltrexone molecules, you can't superimpose them. You have a left-sided molecule which acts on the mu receptor, the opioid mu receptor, and you have a right-sided molecule or dextro molecule which acts on the toll-like 4 receptor and stops the propagation of these inflammatory responses, helping to stabilize the immune system and bring back balance. Remember, diseases, autoimmune conditions, any chronic diseases is all about an imbalance, and all LDN is trying to regain that balance. That concludes today's video. Hopefully you found it useful and I haven't confused you too much. If you like the video, give us a thumbs up, and if you haven't done so already, please press the subscribe button. Any questions that you may have, leave them in the comments and we'll get back to you. Thanks. See you next time.